All right. Good morning and hello, everyone. Welcome to another episode of WESTalks Speaker Series. Um, WESTalks is presented to you in collaboration with the IC Impacts and UBC Future Waters. And we try to host speakers and experts from related to the field of water research. This is the organizing committee for WESTalks. It consists of Abhishek, Fuhar, Layli, and Carl from UBC, myself, Jaskaran from University of Guelph, Kelsey from University of Victoria, and Feria from IC Impacts. So this is a map of where our participants joined from in the past. So I would also like you to please add your location if you are new to this series. So welcome, a very warm welcome to you all. And I'm going to share the link for this map very soon in the chat box. So please, you can add yourself in the map so we know where our participants are joining from. And as we can see, we have a very diverse group of participants in the past, and we hope to have so in the future as well. So this is the lineup for our speakers. And last week, 2 weeks ago, we had Dr. Andrew, who spoke on a very nice presentation on bacteria transport. And this week, today, we have the privilege of having Dr. Michael Bentel with us, who will be speaking on chemical destruction of aqueous PFAS, and he will give us some insights on if PFAS is truly the forever chemical and how we can deal with it. And I would also like to invite the new participants to register on the WESTalks page so that you can receive all the updates on your email and you also never miss future presentation. And also another, this is fall 21, and one change that we had made is now we have the presentations every other week. Earlier, we used to have it every week, so now we have it every other week. I would also like to let you know that we have our previous WESTalk videos, which are available on our IC Impacts YouTube page. I will share the link for the YouTube channel as well on the chat. So 3 links I have to share once the presentation has begun. So I'll talk a little bit about Dr. Michael Bentel. It is an absolute honor to have him among us. Dr. Bentel received his bachelor's in chemical engineering from University of Illinois at Chicago in 2013, his master's in inorganic chemistry and PhD in chemical and environmental engineering from the University of California, Riverside in 2020. And Dr. Bentel joined the Environmental Engineering and Earth Sciences Department at Clemson University as a postdoc in Dr. Ezra Cates' lab, developing photocatalytic materials for water quality applications. And he has been recognized on various occasions by professional organizations, including the Association of Environmental Engineering and Science Professors for the 2021 Outstanding Doctoral Dissertation Award, the American Chemical Society for Ellen Gonter Environmental Chemistry Best Paper Award in 2019, and also in 2019, the Committee on Environmental Improvement Film Award. And the American Water Works Association in 2018, he was also a recipient of the American Water Scholarship. And we would like to thank him for his contributions and towards advancement towards environmental chemistry and water quality. And before I pass on the virtual stage to Dr. Bentel, I would like all the participants to know that you can type in your questions in the chat box in Zoom, so you have access to that. And at the conclusion of the talk, we will have a 15 minutes Q&A session. So thank you, everyone. And with that, I would like to pass on this virtual stage to Dr. Bentel.
Thank you. Thank you. Let me go ahead and share my screen. All right. Can everyone see that? Thumbs up. Thank you. Thank you. Okay. It's great to be here. I'm just moving this box so it's not in my way. Great. Thank you so much for that kind introduction. My name is Michael Bentel, and I am very excited today to share with you this work that I've been doing during my PhD, really, at the University of California, Riverside, on chemically destroying PFAS. And hopefully by the end of this talk, I can convince you that these things might not really be forever chemical. All right, so just a little brief outline of what I'm motivated today is really, I just want to introduce you to what PFAS are, where are they, why do we care about PFAS, but really focusing on these strategies that we use to chemically destroy a number of different PFAS structures. And then I'll round it out with my kind of outlook on the future of PFAS and where I think it's going and its implications with drinking water. All right, so this story begins with perfluorooctanoic acid. It was discovered in 1938 by DuPont, and they quickly realized it and its applications in consumer products. Here I show just a number of consumer products, but really there are hundreds. And a lot of them you can see up there are very critical, such as medical supplies or even our batteries. But we even use them in these kind of different areas like contact materials. This grew to be a very large, lucrative industry, valued at over $1 billion a year. And unfortunately, due to consumer products, our current waste infrastructure, and the use of aqueous film fighting foam, which is a firefighting foam, this has led to the complete pollution of the environment. And this ultimately has provided humans some detrimental effects. So we really want to go ahead and mitigate PFAS in the environment. To learn more about this, I encourage you to check out a documentary or a drama. And just recently, John Oliver had an expose. It was really good. So I encourage you to go ahead and view those. All right, so what are per and poly-fluoroalkyl substances? By definition, perfluoroalkyl substances are any substances that contain only CF bonds that are along that carbon chain. These are just two legacy PFAS, PFOA and PFOS. You're probably familiar with them. And then here's that emerging Gen X with that ether linkage. These are distinctly different than poly-fluoroalkyl substances that contain at least one CH bond. You can see it right here. This is the 3M sort of emerging replacement, and here's are some legacy poly-fluoroalkyl substances. And this distinction is made because later on in the talk, we'll be really scrutinizing these two sort of structures. So currently, when we deal with PFAS in the aqueous systems, this is not really dealt with well. So we clean our water through wastewater treatment plants, and these are typically comprised of very simplistically 2 units of physical separation and a chemical destruction. And so I modeled this little PFOA molecule, and it's going to enter into our physical separation unit, and it actually will be absorbed onto many of these sort of physical separating systems or techniques, I should say. Unfortunately, it creates this enriched PFAS waste, which then we will end up reintroducing to the environment, whether it be through incineration, deep injection wells, or landfills. These smaller PFAS will end up evading these physical barriers and enter the chemical destruction, but primarily the oxidants that we use currently in the chemical destruction phase cannot oxidize the CF bond. So these simply elute out and back into the environment. So this has really given us an opportunity here to explore different techniques that utilize what I will call electron transfer mechanisms to chemically destroy these CF bonds. So that's where I come in. I've been developing this UV sulfite system that relies on this 254 nanometer mercury lamp to basically generate these active radicals. Here I show sulfite under UV irradiation will spontaneously generate the sulfite radical and the hydrated electron. The hydrated electron is really what we're concerned with here, where we believe that this hydrated electron can react with this halogenated organic and then defluorinate. And so that's what I will propose here, this sort of direct defluorination where the hydrated electron is directly cleaving the CF bond. We do generate that sulfite radical, and this would be considered an oxidative radical, and we can tell that by its positive oxidation potential versus the negative reduction potential on the hydrated electron. And so we know that, as I stated in the last slide, that it's very difficult to oxidize CF bonds, but possibly we can maybe use this radical to oxidize other parts on the PFAS molecule, making it unstable and readily available to cleave more CF bonds. But really what this system looks like is this schematic I've drawn here. And you can see a picture of it right here, but it's just a simple glass reactor. You have the PFAS solution in the bright blue, and then the water cooling in the dark blue. And we have the lamp on the inside, and this is a quartz immersion well. Now this is temperature controlled and consistently stirred, and it's buffered at 9.5. our reaction samples are then subjected to a suite of characterization techniques such as LCM-SMS, ion chromatography, and ion selective electrode. And we've also incorporated using computational calculations to sort of interpret our results at the molecular level. So today I am setting out to sort of answer 3 questions. Hopefully I can convince you that these answers are correct. And that first question is, can the UV sulfite system treat PFAS? I've explored several structures, but for today's talk, just due to time, I'm just going to focus on PFCAs, the fluorotelomere carboxylic acids, and the perfluorosulfonic acids. After that, I'd like to really see how far we can push this system in terms of defluorination. And lastly, go to that question of are these really persistent forever? Okay, so let's begin. This first idea of like, what can the UV sulfite treatment system treat, I should say. And so what we're motivated is really understanding these PFAS molecules, fundamentally from a chemistry standpoint. So instead of just exploring 1 or 2 molecules, we looked at 3 different families and several different chain lengths as indicated by the N. And we're really curious about what influences defluorination, what are the paths of destruction, and then can we predict these events? And so to begin, I like to just make 2 definitions: degradation and defluorination. Now, degradation in this context is when a compound has been transformed, and this is typically indicative of some sort of chemical reaction. And I've shown it here in this sort of simplistic chemical equation, but really all we're doing is generating a transformation product. That may or may not generate a fluorine atom, but this just tells us that something has happened. Defluorination is fluoride is present, and this indicates directly that CF bond breakage has occurred. And I've modeled it here by showing that the F atom is here. So these 2 things taken together is a much better approach to understanding these systems. So by first looking at degradation and these 3 different families, we see a trend right away across these 2 selected chain lengths that I've shown here. And it's simply stated, the PFCAs are much more reactive than the sulfonic acids and the telomere carboxylic acids. And then when we couple that with our defluorination results, we see a much similar trend where the carboxylic acids are better at being able to defluorinate versus the sulfonic acids and carboxylic acids. So this tells me that clearly we have different reactivities and different possible mechanisms. But what's even more interesting to me is that we see this chain length dependence with the sulfonic acids and the carboxylic acids. And this indicates to me that there might be something special going on with this carbonyl group connected directly to the perfluoroalkyl group. Whereas if there's a separation or if it's connected to something different, maybe there's another mechanism going on. And so our approach in looking at all these different compounds, all these different lengths really came to fruition when we came across TFA, or trifluoroacetic acid, where we found 100% defluorination. And this really opened up our eyes to what we should be looking for in terms of mechanisms. I don't have time to go into those studies, but I will summarize them here. And so we know that there's reactivity across different families. But what we really found out is that there's distinctly 2 defluorination pathways. Especially for these perfluorocarboxylic acids, we can undergo this sort of chain shortening mechanism where we activate the PFAS and we go ahead and oxidize it to generate not only 1 fluorine atom, but 2 fluorine atoms and get the chain shortened product. Of course, another route that can go is this direct defluorination, or this HF exchange, where we're actually just exchanging 1 CF bond for a CH bond. And all compounds can undergo this sort of defluorination mechanism. And like I said, I didn't have time to demonstrate this sort of method that we came up with, calculating bond dissociation energies and how they might be able to predict defluorination events. But I will showcase this in some slides later on. But we were able to do this, and we feel very proud about that. All right, so let's move on. So now that we understand our system a little bit better, we really want to know how far can we push this forward. And when we think about this, at least for me, I think about this in terms of chemistry. And really, I want to focus on those 2 defluorination reactions, this HF exchange versus this chain shortening. And is there some competition? And if so, can we control it? And so what motivated me really was, how do I get more defluorination? And to get more defluorination, my one thought was, I need more sulfite. And if I have more sulfite, then I can generate these reactive species. So I don't see there it is. Okay, so when we look at the sulfite speciation at 9.5, we can already tell that we're basically predominantly in the sulfite regime. So I know I can't make any more sulfite by going to higher pH. But I'm also interested in the hydrated electron, because the hydrated electron can go ahead and directly defluorinate. So, going back into the literature and you go back several decades, you can find out that, well, the hydrated electron can actually increase its lifetime at higher pHs. And if it can increase the lifetime, can I maybe then have it stick around long enough to react in a defluorination event? And so I was really motivated by that. And then I found out, just thinking about thermodynamics a little bit here, excuse me, that's a little bit premature. This hydrated electron can be scavenged by these protons. And if we simply just go to a higher pH, maybe we can go ahead and regenerate any scavenged protons as well. So really, this is sort of a thermodynamic balance. And I just bring this up here because I thought this was interesting. A colleague of mine several years ago, we were thinking about this and they thought maybe it was a bisulfite scavenging. And though it does appear to scavenge hydrated electron, it might not be the principal thing that we're interested in, but I just thought that was interesting. All right, so let's test this hypothesis. And by doing that, we just simply increase the pH. And by looking at PFOA and increasing the pH, we see clearly much better defluorination. What I think is really interesting is that when going from 9.5 to 12, we really seem to expose this sort of sharp slope before giving way to a much more modest defluorination. And that might indicate to us two competing mechanisms, two regimes in which these reactions are happening. I then took that pH 12 and I screened several sulfites concentrations because I was just curious to see maybe, are we more efficient? And that indeed is the fact. By just simply comparing this 10 millimolar blue line with the 9.5 over here, which is also 10 millimolar, we see that we have much greater fluoride release at the same sulfite concentration, which means sulfite is being utilized in a much more efficient way. How? We're not sure exactly yet. I'll tell you in a second, but for right now, it's being utilized much more efficiently. And if you're not convinced, I redid this experiment at pH 9.5 and I just put in 50 millimolar sulfite. And clearly I cannot achieve what I've achieved at pH 12. So at the very base level, from a chemical standpoint, something different's going on. We demonstrate this on a row or a list of PFCAs, and we see that we have extensive defluorination. We've increased our degradation kinetics by 10 times, and then we've actually decreased our EEO, our electrical energy consumption per unit volume, on order of magnitude. And why we're interested in this is a very easy brass tacks number to equate apples to apples, different treatment technologies. And so really where you want to be here is around 1. We obviously are about a factor off of that, but we've definitely made extensive progress. And so I want to really highlight this competition between chain shortening and HF exchange. And to do that, I like to look at the products. And so here is the products from the pH 12 reactions. And all I need you to see is that the dominant product here is the chain shortened product, and the minor product is the HF exchange. We see several more products, but they're very low in concentration. So these are really the governing mechanisms happening. When we directly compare this to the pH 9.5, we see the exact opposite. The HF exchange is now the dominant product, and chain shortening is the minor product. And to explain this, let's go back to our thermodynamics. So at a lower pH, we have higher concentration of H+, it will be scavenged, and then it will introduce the H dot atom. The H dot radical here will combine in the HF exchange reaction and promote this production. But if we go ahead and increase the pH, we can mitigate the production of H dot and really drive the chain shortening. And that's how we can explain this. I do want to tell you, though, that we have achieved our goal of increasing the lifetime of the hydrated electron. And that's clearly demonstrated in the number of HF exchange products we see. Now, of course, these are very low concentration, but these demonstrate that, in fact, the hydrated electron is the active species at higher pH. And clearly, we have more HF exchange products at pH 12 than we do at pH 9.5. So just in conclusion, by simply changing the thermodynamics of the system, we've improved the efficiency and the effectiveness. We have incredible degradation rates shown here, really good defluorination or fluoride recovery. But at the end of the day, we want cost effectiveness, and that's we're driving towards that. We seem to go ahead and elucidate that there is this competition and that we can control this competition and that we can enhance the lifetime of the electron. Okay, so moving on to this last topic is this sort of switching gears here. We've been talking about UV sulfite this entire time. I want to talk about oxidation a little bit. So this is some work that we did and we just released earlier this year. And really what I want to set out and kind of ask is, what is the role of oxidation in these units or in this sort of technique? And is recovering 100% fluoride achievable? And we're going to focus on the sulfate radical and the hydroxyl radical, because these are just two very common advanced oxidation processes. All right. So the motivation here, if it wasn't clear, is that we can't seem to achieve 100% defluorination at pH 12. We know that these HF exchanges are inevitable. And if it's inevitable, we know that we will introduce these sort of methylene groups or ethylene units. And we know from our FTCA studies that short chain fluoroalkyl groups are very difficult to directly defluorinate. And to demonstrate that, I have a table here showing some fluorotelomere carboxylates, fluorotelomere sulfonates, and we see very sluggish results, and as well as sluggish results for the sulfonates. And this really tells us that we need that carboxylate directly bound to the perfluoroalkyl chain to get that really good defluorination. And so this is highly desirable. But this idea of oxidizing these organic constituents isn't new. And honestly, we've known about this for years. This has been observed in nature. AFFF, that firefighting foam, will oxidize in nature to generate these PFCAs, these perfluorocarboxylates. And of course, this has been actually pioneered to be used as an analytical tool to actually measure the contamination of soil from PFAS. So this is nothing extremely new, but let's see if we can combine it and really maximize our effectivity. All right, so we'll begin with this showing you how we generate these sulfate radicals. We use persulfate and we throw it into a pressure cooker. This is just a rice cooker, and I mean, this is what we use. And at pH 2, we can exclusively generate this sulfate radical. Now, if we increase it to pH 12, we introduce that hydroxide ion, and then we can go ahead and exclusively create or generate the hydroxyl radical. And so now we can use these two techniques to really probe the effects of these two oxidants. And we are going to demonstrate that by using this model compound, this N=6 fluorotelomere carboxylate, and starting with the graph on the top. These are, this y-axis is normalized to the initial loading of that fluorotelomere, and we're seeing the product distribution. And so what we see as we increase the amount of oxidant, we actually not only change the product distribution as can be seen here, but we're actually destroying more of these products, these PFCA products. This is obviously in direct comparison different than what's going on with the hydroxyl radical, where we see the product distribution is very similar, even though we're increasing it on the oxidant loading. To explain this, I go to the literature. And this is well known, well established, that the sulfate radical is a very powerful oxidant, 2.4 volts, and it can undergo a 1 electron oxidation, and it does the chain shortening to generate some fluoride. But it's effectively destroying PFCAs. Now for the hydroxyl radical, why don't we see that same thing? So to prove this, to probe this, I should say, we took PFCAs and put them back into the pressure cooker with our hydroxyl radical, and to see how much defluorination we get. And we see no defluorination. But we knew this going into this because we know the CF bond can't be oxidized. But this also indicates that the carbonyl cannot be oxidized as well. So what I want to point out here is, even though the sulfate radical is a very strong oxidant and can destroy PFCAs, the hydroxyl radical at its lower potential cannot destroy PFCAs, but can effectively oxidize. Now, where this gets more interesting is when we start to look at the kinetics. So to really demonstrate this, I'm going to change it just a little bit. I'm going to use the N=6 fluorotelomere sulfonate. But let's take a look at the results. Starting with the graph on top, starting with this left axis. This is the parent degradation percentage, or what percentage of the parent compound did we degrade. As we increase the oxidant loading, we are effectively increasing the ability to degrade these fluorotelomers. And that's very good, very happy about that. But then I come down to the hydroxyl radical, and I look as low as 10-to-1 oxidant loading. I have almost 85% parent compound degradation. And by the time I get to 20, I have complete parent compound degradation. How do you explain this? The sulfate radical is a much powerful oxidant. Clearly, it should be better. And when we look at the kinetics of the sulfate radical and the hydroxyl radical, and I just selected some alcohols right here, we can see clearly hydroxyl radical is much faster. And so just to really highlight this, I've cherry picked the ethanol and the N-propanol because it kind of looks like a fluorotelomer. And we can just see that this hydroxyl radical is better as a hydrogen abstraction radical or oxidant than the sulfate radical. But I want to turn our attention to the defluorination, because this is very interesting. I look at the sulfate radical, or I look at the sulfate radical, and we see 8% defluorination, and we know this because it can destroy PFCAs, and we can see the fluorine release. But then I come down to the hydroxyl radical, and I see 50%. I've gotten 50% of my CF bonds have already been cleaved just by simply subjecting it to the OH dot, but we cannot destroy PFCA. So what is going on here? What have we kind of stumbled upon? And so I'm going to try to explain this to you the best I can, and hopefully I can convince you of this mechanism. And so I have this fluorotelmer, and we used our computational skills to calculate the energies of these two methylene groups. And we see the one closest to the carboxylate is much lower, which indicates the probability of this bond being cleaved much higher. And so following the blue pathway, we can go one of two routes. We can go route one, which, if it pops up, there it is. Route one will oxidize this H atom, and it's going to generate this carbene anion, relatively unstable, and ultimately generate the N chain product. Now, conversely, going from that one spot, if we can fall the other way, we can generate this alkene carboxylate, and this alkene carboxylate will fall apart and generate the N-1 product, cleaving two CF bonds along the way, which we're very happy about. Now, if it doesn't go the blue route, it's going more uphill, taking the longer road. It's going to go to this red path, and path 3 will oxidize, and we'll have the same formation of another carbene anion, relatively unstable, but that fluoroalkyl chain is going to be right here, and this radical will react with the hydroxyl to generate the N-1 and generate more fluoride. We can go down the fourth pathway, which again, just the electron really just falling the other way, and we generate that poly-fluoroalkyl carboxylate, which will become oxidized in our system, generating more fluoride, and then generating the N-2 product. Now, what's interesting here is when we look at the product distribution from this reaction, we don't see what we see above. We do see the primary N-2 product across all chain lengths. We see the very small N product generated through path 1, but we see N-3, we see N-4, we see N-5 products. And the way that it's drawn right now, we cannot rationalize that. So this is where I introduce this beta fragmentation. And when we generate these perfluoroalcohols in situ, we can go ahead and oxidize it to generate this perfluoroalkoxide radical. This will spontaneously fragment into the difluorocarbonic acid, which falls apart in water. And then we regenerate that perfluoroalkyl radical, which will undergo hydroxylation, and then the cascade begins. And so this can be summarized here, where from path 1, we just get the N product, the very minor product. From paths 2 and 3, we get the N-1 product. And then from paths 2, 3, 4, we get the entire slew of chain lengths, and which really kind of highlight that perhaps 1 and 3 are very unfavorable, and 2 and 4 are favorable due to both the thermodynamics of the CH bond cleavage and the transformation product generation. So let's combine all of this together, and let's really demonstrate this in practice. So we take these PFCAs, and we can go ahead and put them in our pressure cooker, and we get all this fluoride in orange. And we get some of these PFCAs in blue. But we know with our UV sulfite system at its optimized conditions, we can just keep cleaving away. As long as those bonds are green, we can start cleaving. And then when they get more difficult, they take a little bit slower, but we start to cleave them. And sure enough, we get these species that have a bunch of CH2 units, and we know that those are readily cleavable. So we just do it again. And so when we do this sort of cycling of oxidation, reduction, oxidation, we can see at least up to our N=6 that we have 100% fluoride recovery. To demonstrate this even further, we started just with the parent compound PFCAs, the perfluorocarboxylic acids. At step 2, we just started there, and we subjected it, and we got 100% fluoride release from all the perfluorocarboxylic acids and perfluorosulfonic acids. And as I mentioned briefly earlier, in the environment, typically these compounds will transform into these very stable perfluorocarboxylic and perfluorosulfonic acids. So this is very, very promising for us. And so I'm just going to go ahead and summarize everything that we've talked about in terms of our strategies with this question of these forever chemicals. And so I didn't have time to go over the emerging ether compounds, but we looked at these legacy compounds and really started to understand the mechanisms going on in this system. And we highlight 2 of them that I categorize based on CF bond dependency. And we have the ideal mechanisms where these chain shortening mechanisms, again, I could not go into detail about this, but we can talk about it afterwards. But these two mechanisms are labeled or able to cleave any CF bond, primary bonds, secondary bonds, strong, weak, doesn't matter. And this is the route that we want to go down. But we can also take advantage of cleaving bonds directly with the hydrated electron, but this is definitely energy dependent. We were able to go ahead and, when we understood our system, to take advantage of some thermodynamics and really push this system to its limit and really get some deep defluorination, which made this strategy possible. It was because of the unfortunate HF exchanges that oxidation is such an effective strategy, not only on the perfluorinated or the poly-fluorinated compounds that already have the CH bonds, but on our reduced products that introduce the CH bonds. And then we found out that hydroxyl radical is a little bit more magical, I guess, as an oxidant than the sulfate radical, even though it's not as powerful. And then I guess I will go ahead and kind of just give you what I believe is the future of PFAS in two different regards. First, in terms of research, I see it changing, but right now it seems majority of people focus on certain structures like PFOA, PFAS, Gen X. These are very famous, everyone knows about them. But I hope I was able to demonstrate that by looking at them as classes and really interrogating them across all chain lengths, you can really start to elucidate what's going down at the chemical level. And this goes directly into my second kind of critique of the research, which is the way that we evaluate things. And I use this picture of the president. This is President Truman, who is holding up a paper that declares that he lost the presidency, though he was our president. And this is what I think we do often in science. We destroy PFOA. Right, I showed you earlier that degradation where we transform it into something else, and then we say, "Look, it's gone. I've won." And I think I've tried to stress that we really need to be focusing on fluoride. We need to be focusing on the CF bond breaking. That is the only true measurement that we've mitigated any risk to both humans and the environment. And then a little bit more broadly, we use these in a lot of applications, and we like that. This is demonstrated by its market share. A lot of people are willing to pay a lot of money to make these products. And I think that a lot of them are essential, or not a lot of them, but some of them are essential. Pacemakers and other medical devices, absolutely. I just don't know if we need them in our floss or in our ski wax. I'm just not sure that cost benefit is there. So something to think about, especially as you take a look at drinking water. This was a paper from 2020. And it is sure of predicting what level of exposure PFOA and PFAS is in our drinking water. And they predict that basically everyone in America is drinking some level of this. And this is concerning to me because we've stopped manufacturing these compounds in America for close to 20 years, and they're still here, giving this moniker of the forever chemicals. But I think we demonstrated today that they're not forever if we just design the systems correctly and understand the chemistry. And so with that, I would like to go ahead and acknowledge some important people that helped with this work. Of course, my advisor at UCR, University of California, Riverside, our collaborators both at UCR and UIUC, my lab mates and undergraduate research assistants that helped in this research, and of course, my funding sources that allowed me to do the research. And I will go ahead and conclude with this picture of Yosemite National Park I took right before my dissertation. And I'd happy to ask any or answer any questions. Thank you.